So let's review cis and trans isomerization before getting back to our double bond positioning. We've talked about cis and trans isomers, which are geometric isomers. They are stereoisomers. Remember, I'm saying all of these words. Remember what these words mean. Stereoisomers, and they are diastereomers. They are not mirror images. So we've talked about having cis and trans isomers in rings, in just simple rings, no double bonds. And that's because these rings are sterically hindered when they are small, and they cannot rotate around the carbon. And so they technically have two different isomer positions. Because they are locked into their ring position, you can have, for example, in this ring with two chlorines, both of the chlorines facing up, or one chlorine facing up and one chlorine facing down. Then we talked about how these have different properties because they are diastereomers, and these are only different because of their positioning in space. We also talked about naming these types of ring isomers, where cis means that the groups are on the same side, and trans means they are on opposite sides. So cis would be when both chlorines are on the same side of the ring, and trans would be when they are on opposite sides of the ring. The rules for cis and trans, we can use these words, cis and trans, as long as two carbons have at least one identical substituent. This is key. One identical substituent above or below the ring. So in our example here with this cyclobutane, it has a methyl group and it has an ethyl group attached to it. These are different from each other, but it also has a hydrogen and a hydrogen on each of these points. So because the hydrogens are the same, we can use the Cis Trans Nomenclature. So in this case, our groups that are different are on the same side, making this a cis. Over here, the groups that are different are on opposite sides of the ring, one up and one down, and so this is trans. Cases where you cannot use cis and trans isomerization. For example, if only one carbon with two different groups above and below the plane. So for example, here, we do have two groups that are the same on each side, but on the same point of a carbon, we have groups that are identical. So again, you have to have on the 2 points you are comparing, you have to have a set of groups that are the same, be them hydrogens or in this case methyl. But when looking at the point itself, the two groups have to be different from each other. Here you can see that even if you moved positioning of up and down, you just have the same molecule. That's why cis and trans will not work for this case. Or you cannot use cis and trans when you have 3 or more carbons in a ring that have different substituents. The reason for this is there's too many possibilities. You can't have just cis or trans. And in fact, you will be using a new system, which we'll talk about today, called the R or S distinguishing. So again, this type of isomerization using cis or trans is also possible in alkenes when we have a double bond. And that's because just like in our ring, in our strained small ring, there's no rotation along a double bond. Remember that single bonds can have conformers, and these are generally identical molecules that have different conformations. And these are possible because of the rotation around a single bond. These all have identical physical properties because they are essentially identical molecules. However, with double bonds, you do have actual isomers, geometric isomers. And that's because these are technically different molecules because you cannot interconvert between a double bond at all without breaking the bond. These thus have different physical properties. Just like with our rings, cis exists when you have your groups on the same side, and trans is when they are on the opposite side. Again, the minimum requirement for cis trans is that each carbon is bonded to two different groups and that two of the carbons have at least one substituent in common. Again, to see this in an easier manner, we've labeled things with A's and B's. So when you look at the individual carbon, they have to have two different groups, an A and a B. However, when you look across between the two carbons, there has to be at least one shared group. So both A's, or here also both B's. Cis trans isomerization is not possible if two groups on one carbon are identical. So for example, if in the same carbon you have identical groups, you can't do cis trans isomerization. And again, substituents that are on the same side are cis and on opposite sides are trans. What about double bonds in rings? Double bonds can be found in rings of all sizes, with the smallest example being a cyclopropene. These double bonds are named just as we talked about before. You can still grant cis and trans isomerization to a double bond within a ring. Small alkenes in general are so small that universally they contain cis double bonds. They just can't rotate in a way. It causes so much strain if they were to have a trans double bond in a ring. So for ring sizes 7 and below, it's safe to just ignore writing any conformation and just assume that it is a cis double bond because of the ring strain. However, when you have ring sizes of 8 and above, you do need to put cis or trans in the name because there is technically the feasibility of a trans isomer. So the energy difference and that strain differs and diminishes as you get a bigger and bigger ring with a double bond. Here you can see in this ring, our groups are opposite of each other. The hydrogens are opposite of each other, one up and one down, and so they are trans. Whereas here they are both on the same side, so they are cis. Generally for rings, the cis conformation is going to be the more stable conformation.